Yours?
Yes.
Right.
It's somewhere.
Yeah, I haven't looked it up.
It's just somewhere. That's my copyright somewhere.
Right.
That's my copy.
It is. No, it's lovely.
So what does
The arrow keys
do for us?
Or doesn't.
The arrow keys were
Fantastic. Yeah, that's me sorting. I walk into that. Good. Okay. Ready to go.
Okay, we are starting. So everybody on Zoom, please grab your cup of tea or coffee silently. We've just had ours.
Water.
Water, fine.
Fine water.
Yeah. Okay, it's my pleasure to introduce John Willliamson, who is going to talk about what quantum relativistic mechanics can do for us. Right?
Right.
Thank you.
Good. Couldn't have put it better myself. Yes. So that's what I want to do today is talk about the effects that the major theories in physics have on the reality in which we live, how it conditions it, how it forms it the way that it is, and the how and the why of that. So what I'm going to do is I'm going to start with space and time, and then talk about not just space and time, but also another space and time, inverse space and inverse time, which are in some ways more important because it's in the realm of inverse space and inverse time that we exist, not in space and time. Because existence implies having some content, and that content is given through vibration. And vibration is a frequency, and energy is Planck's constant times frequency. So there is a sense in which energy itself is just a vibration of space-time. It's the inverse of time that we're talking about when we're talking about energy, and the inverse of space that we're talking about when we're talking about momentum. So these are the first two things to bear in mind. They're called reciprocal spaces, and these are things that are used very widely in one of the fields I was active in solid state physics, but are kind of less familiar in terms of high energy physics and the particle physics and the nature of those things. So space, time, and relativity, how space and time form into one another to produce things which we call energy and momentum. Relativity is the structure of that space-time. The structure of that space-time has this three-dimensionality of space and this one-dimensionality of time, we think, but they're not separate things. They're all one thing. They're one thing which is connected through and through in terms of the things of which we are made, in terms of the elementary particles, the atoms, the molecules, the crystals, the brains, the quantum mechanics of all of that. How does that all flow through? How does that all come into being? And can we describe it? Can we comprehend it, being part of it ourselves? And how far can we comprehend it? Now, I don't think we can comprehend it completely, but I want to explore that and see how far one can get. So my thesis is going to be that reality is not so much in space and time, but of space and time, and wrapped up in space and time. And keywords throughout the talk are going to be such things as systems are resonant. They are harmonic, they are self-creating, they are things which reform themselves periodically. They are PM things, plus minus things, because they go plus, and then they go minus, and then they go plus, minus, they vibrate. In fact, sometimes they vibrate in more than one direction at once. They vibrate in this direction too. And if they do both, they go round and round in circles. And this is essential. This round and round in circlesness is the essence of quantization. Things are quantized because a worm or a Ouroboros must bite its own tail and then continue. It has to go round and round. It has to recreate itself every fourth differential, if we want to go into some maths, but every fourth turn of the reons. You come back to where you started from. Things go round and round in circles. How about not just circles, but also spheres and also tori and also hyperspheres? So it's a little bit more complicated than just a two-dimensional rotation, of course, in reality. Look at it. Can't you tell? It's not two-dimensional. It's a bit more than that. So we're going to talk about what this Rubik's Cube thing here is talking about, and we'll come back to this later, are the combinations of space and time, the way space and time wrap up into one another. So if we take any dimension, x, y, z, or t, and multiply it by itself, then we get a scalar object, which is a different kind of object to the vectors of x, y, z, and t. That scalar object lives in a different, linearly independent dimension in a sense. So we have a four-dimensional space-time, but some objects in that four-dimensional space-time have the character of a scalar. This is a fifth element. And that fifth element can be thought of as being, well, energy as well. That could be, and you'd say that fifth element is related to the inverse element, as I already have, time, frequency. So how these things fit together is a jigsaw, a multiple four-dimensional jigsaw, which ends up coming together and producing something that looks very, very three-dimensional. It's more complicated than simply and only three-dimensional. It's multiply three-dimensional in my view. But it looks and is, and we can walk around three-dimensional space because it's constructed of these things in a three-dimensional way. So what these things are is the colors are here are supposed to be roughly these colors. So the yellow type things are actually a complex energy. They're the scalar and the dual scalar, the pseudoscalar. They're kind of yellowish. There's one here and then one here. Then the vector things which generate the algebra are time, space, space, space. They're kind of in orange, these things over here. Then we have things which, if we have a space and then we extend that space, we multiply it. What does multiplication mean when you, or division? What does division mean? I mean, division, we know what division means. You know, 6 divided by 3 is 2, one of them. But what does it mean if you take something like a ruler, a cubit, and then divide it by a clock? If you divide space by time, is that space? Is that time? Well, it's neither, it's velocity. Space divided by time. It's a two-dimensional thing. And if I take something in space and then I multiply it by a perpendicular space, well, we know what that does. Any carpet layer will tell you that gives you an area. And an area is different to a vector. So that's what these things are up here. They're multiplications of one space by a perpendicular space. And the objects which we're going to talk about have dimensionality in that kind of way. They're not vectors. They're in the nomenclature of Clifford algebras, they're bivectors. These things are bivector elements. And an example of a bivector element, which is space-space, is the magnetic field, because it's the spatial derivative of a vector thing, perpendicularly. The magnetic field is in that kind of direction. It's not. BZ is not in Z. It's entirely not in Z. It's perfectly, completely in the XY plane. So it's an axial vector. There's nothing in Z at all of a Z magnetic field. It's all an XY plane. It's a rotation in the XY plane. And that's what a magnetic field in Z does. In comes an electron. Guess what? It rotates in the XY plane. It's blindingly obvious if you start looking at experiment, which we need to do when we're doing physics. Relate everything to reality. And if it doesn't fit reality, your theory's got a problem. So that's what these things are, the space-time planes. And these next things, they're they're space-space planes. The next things are space-time planes. Now, space-time planes, kind of things that are in space-time planes, well, one of them is the electric field. Sorry, I'm moving out of the camera. One of them is the electric field. The electric field is defined as the derivative, the time derivative of the spatial part of the four-vector potential. So that's a space divided by a time, like velocity, like velocity or momentum. And it's in a bivector direction of space divided by time, or space times time. Same direction. Oh, yes, I should say about inverse of these things. Everybody knows what the inverse of a vector is, don't you?
No.
Right, okay, so I better tell people what the inverse of, actually, I must say that I don't know what the inverse of a vector is, but I'm going to tell you anyway. So the inverse of a vector actually depends on the metric. So if we take a vector algebra where x times x is 1, then this is a 2-qubit vector, qubits that bit, so that's a 2-qubit vector. The inverse of that in vector algebra is a half-qubit vector. So what the inverse is, if I multiply something by the thing I first thought of, I get 1. That's an inverse. So it's a vector in the same direction, but half the size if it's 2 units long, or a tenth of the size if it's 10 units long. That's the inverse of a vector. Now, however, the reason I say I don't know what it is because I don't know whether my metric is plus, minus, 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 or minus, plus, plus, plus. And if it's plus, minus, 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 which I suspect to be the case, then the inverse of that vector is not this vector here, it's the one going negative. Of course, that gives me the number 1. So take your pick. I prefer the second choice. I'll go for that one if I had to make a bet. And these things likewise have inverses, but those inverses are a little bit more complicated. Now, it's so much more complicated that I wrote a paper which I published last year on that. So if you want to read that, it's up on my website. The website, by the way, with all this stuff and lots more is quisicle.com. Quisicle is a 4-dimensional quantum bicycle. So it's spelled just like bicycle, but instead of the B, you put QU for 4, quisicle. So it's all up there. The papers are up there. So if you want to read more, please feel free. Now, this work was not done in isolation. I must credit some people. And I will particularly like to credit my current working group, which is the Quisicle group. We meet every Friday usually and have a little chat over several different continents. These are the guys down here. The most important person I want to credit is my friend and co-worker, Martin van der Mark, I worked with for 30 years and who died a few years ago. So this work is, anything credit-worthy in this work is 50% at least due to him. So, right, we can go on to the next slide. Let's press a button. Oh, okay, that's the contributors. So also there are people in this room, you'll find your name, some of you will find your names on that piece of paper as well, who have contributed to my understanding over the years. So it's just a bunch of people who've done. Right, so what are we going to do? We're going to use the basis to try and extend relativity into the quantum mechanical regime. The idea is to try and find the mathematics of reality, where you have a correspondence for what division means, multiplication means, what the elements mean, how they act, how they interact. I want to find that mathematics, which is isomorphic to reality. Now, this is Hilbert's 6th problem, and it's one of the unsolved problems in physics. And I'm afraid it's also unsolved by me. So in this sense, it's a work in progress. But that would be the perfect mathematics to base all this stuff on, because then you could do no wrong. If you had the mathematics which precisely parallel reality, then anything you calculated would also be reflected back in reality, and reality would parallel the mathematics and mathematics to reality. However, this is an attempt to do that insofar as I am capable at the moment, to go as far as is possible. And it's not an attempt this morning or this week or in the last few years. This is something we've been working on for decades to try and refine and change and develop that. But I'm going to start with space and time in the proper relativistic form. So I'm going to take time to be positive unit vector and space to be minus x, minus y, and minus z. And I'm going to use, I call it a Dirac metric, because it's the one that he used. But I'm going to do something more than that. I'm only going to allow myself to write down things in the algebra which I create, which have their proper space-time form. I'm not going to put any mark on paper which doesn't correspond precisely to either space or time or combinations of space and time. So if something comes onto paper which doesn't have that form, then it's not within the mathematics of reality. So that complicates things a lot. It makes life much more difficult for you in a very, very beautiful way. So the hope, of course, is that if one tries to get something which closely corresponds to reality at the base level of space and time, that anything that you create in that will be close to what reality actually does in terms of experiment. That's the hope. Now, as I already said, space-time exists, apparently, but it can be empty, and it mostly is. It's not 99% empty, it's 99 and a whole bunch of nines empty. And you can't write pieces of nines down on a standard piece of paper, just try it. Have a look at how much is empty space even inside an atom. So in a lot of space is just space, there's nothing there. So it's mostly empty. To have something in it, it has to have some energy in it. It has to have something in it. And as I've already said, I think that energy can be associated with the inverse space of space and time, perhaps. But that's not a part of the mathematics. That's something I've made up. Okay, that's what you do. That's what we theorists do. Don't let anyone tell you anything else. We make shit up. And then what we do is we have a look at the stuff and think, well, you know, it doesn't have any correspondence with reality at all. And insofar as it does, then it's a useful thing. So here we are. So quantum mechanically, energy is Planck's constant times the frequency. And momentum is also, it's h bar k, it's times the inverse spatial vector times h bar is the momentum in standard formulations of quantum mechanical theory. So this is what's in the, perhaps not the first undergraduate textbook you come to in, but maybe the second one, slightly more advanced level of quantum mechanics. Right. So what about, now what I want to do is I want to get into the things that make up reality. And the two kinds of things I'm going to talk about are light and materials. But materials from elementary particles to atoms, to molecules, to crystals, to the universe we sit in. That's the idea, trying to say how that flows up and down into the reality in which we live. But I want to start with light because in many ways it's the simplest thing. And also it contains one of the most profound things that influence the way that we see the universe. So what is light? Well, stuff we're all seeing each other with. A lot of us know quite a lot about light and that it's governed by Maxwell's equations, but the light comes in photons, it comes in lumps, so it's quantized as well, which is not in Maxwell's equations. And here's a representation of a single wavelength of a photon, green electric, blue magnetic, energy given by h bar omega, or h nu, Planck's constant times the frequency. Now, all circularly polarized photons have the same angular momentum, h bar. They get it. What's happening if I take light and I squash it in some way? So I take some photons and I thermodynamically compress them so they get more blue. As I'm increasing their energy, what I'm doing is I'm winding them up. I'm making them vibrate more quickly. Now, when things get bigger in energy, photons they get smaller in size. Why? Because they're going round and round. And if I have an arm which is 3 times 10 to the 8 meters long, and I move it round and round at 1 hertz, the ends of my fingers are moving faster than the speed of light. That can't happen. So there's a thing called a rotation horizon, which takes the size of things perpendicularly, and the elements of the photon wave function must compress relativistically as you increase their energy. And what happens is that compression is inverse linear, and the energy increase is linear, leading to the same r cross p angular momentum for all photons. So all photons have the same angular momentum, different energies. So the more energy, the more vibration, the more you shake things up and you wind things up, the more energy you have. The smaller everything gets. Big is small and small is large. Big energy, small size. In the quantum world, I mean, not in, clearly, I mean, if you eat more potatoes, you're going to get bigger. So it doesn't work for potatoes, but it does work for quantized systems. So there are 2 worlds then that are base worlds. One is the world of extent, the things that move away from you, which I can count by taking my photon and saying, oh, it's 10 to the 7 wavelengths. So therefore that's a end of the building down here. I could count the number of cycles, that's an extent. But the thing I'm using to count that is an inverse extent. It's something which is periodic, which is a wave. I can imagine having a ruler which has got marks on it every time I reach a crest or the bottom of a wave, and that's my ruler. My ruler. In order to divide the world up and learn how big it is, we need to look at it, something which gives us the inverse of that. And we say so if we want to measure how big something is, we take a ruler and we say, how many rulers does it take to go into this room? And then I divide the number of rulers by the number that go into the room, and I get whatever it is, 20 meters. Right. So, right, next slide. I want to talk a little bit about quantum electrodynamics. Now, I'm not going to go into the theory of quantum electrodynamics. You'll probably be quite happy to learn, but I want to talk about what it does for you. So electrodynamics, space and time, what do we have? You see, as you go faster and faster, or as you accelerate things, they get smaller and smaller. Now that goes for space and time itself. If we're talking about putting energy into something, what happens is that your scale of length and time changes. And as you approach the speed of light, then any distance becomes no distance at all. The equations are such that the distance between 2 objects connected by a light ray, the interval, ct squared minus x squared minus z squared minus x squared minus y squared minus z squared is 0 for all light paths. They're at the same point in space-time, emission and absorption. Now, think about that for a second. What's happening is that there are three sun's coming in through the window. Look, this is mine. That stuff is coming from 8 minutes ago's sun. That stuff is just impacting on the back of my trousers. It's been traveling for 8 minutes at light speed in my frame and in the sun's frame. However, that frame is not symmetric. I'm emitting as well. I'm 300 K. I'm emitting warmth that you can feel the warmth. I'm sending things out. Now I'm getting stuff from my cast, the sun, and I can feel it. The sun doesn't feel me. It doesn't feel me at all. But it has sent those photons to its future, hasn't it? Those photons were absorbed 8 minutes later, according to Mr. Sun. Or should it be, no, I don't like Mrs. Sun. That doesn't sound right, does it? Mrs. Daughter might be okay, but Mrs. Sun, no, Mr. Sun. Right. Okay. Unless we're in German. Yes, you're right. Kann ich euch in Nederlands doen als je wil? Should we do it? No, okay. No. So that sun's coming in. However, that's two frames, sun frame and John frame. But there's a third frame, which is light frame. And for light frame, those photons were emitted and absorbed at the same point. My trousers were on the sun, and the sun was on my trousers. Luckily, they weren't too close to the sun, so otherwise I'd be in serious trouble. But nonetheless, those connections are there. However, the stuff I'm sending out to you guys, the 300 Kelvin radiation, which is going out there, is going from my present to my future. And for you, it's coming from your past, 3 nanoseconds. A foot's about a nanosecond per foot. Light travel is almost exactly a foot in a nanosecond. So, right, so light speed, the Lorentz contraction, reduces the entire universe. So if you go out on a starry night and looking at the universe, that current universe for you, with that light, which is 0 distance for you, with your eye in those stars and those stars in your eye, are all at the same point, the cutting edge, the pinnacle of space-time, which is your present existence. Everything you perceive is in your past, and you don't perceive the stuff in your future. I can't feel the heat going to you. I can feel the heat coming to me from the sun. That's the arrow of time. The arrow of time is energy from to, start to finish, at the same point in space-time for light. These are quantum electrodynamic transitions of light. So change photon, both things are at the same point as space-time, I've said that. So that present moment is really just the pinnacle, is a very complicated little point, a 3-dimensional point. 3-dimensionality that you perceive of the universe, and it is 3-dimensional, not 4-dimensional, is because stuff is coming in theta and phi to a head, which you have as a size, which you use to give an idea of a scale, which you're interpreting the size of the universe. And believe me, it's a lot bigger than you think it is out there looking at it, what it seems to be. It's certainly a lot bigger than the medieval view of how big that starry sky was, of what you perceive it to be. So the result that you have by looking at the universe with light is a 3-dimensional view of the universe. Dang, 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 and all the stuff coming in and pinching in different directions, not a 4-dimensional view. And it's not a 4-dimensional view partly because one of the dimensions has been lost in the CT squared minus Z squared of the interaction of the photon. But also the 3-dimensionality has been lost because the things you're looking at it with are 3-dimensional in a 3-dimensional space, because the photons are in field space, which is magnetic field space, 3 dimensions, not 4, and electric field space, 3 dimensions, not 4. That's always been the case. There are no 4 dimensions of electric field. And it's electric field that's forming this lectern in front of me. It's 3-dimensional. It's held together by interactions that are electromagnetic. Not 4-dimensional. Look at it. It's not 4-dimensional. I can go 3. I can't do backwards in time. So although space-time is 4-dimensional, that doesn't mean we live in a 4-dimensional world. The world is three-dimensional, but it's multiply 3-dimensional. This is steel. So it's got a magnetic field, 3-dimensional. It's got an electric field. That's what you just heard. The electric nail going against my electric surface of this electric lectern. So, and then producing vibrations which were transmitted through an electric field. All of that, three-dimensional. So this is how the quantum world is conditioning the world that you live in visually. It's turning it to what looks like a three-dimensional world, but it's not three-dimensional. Three-dimensional electric, three-dimensional magnetic, three-dimensional extensive that I can measure with rulers, and 3 dimensions of spin. There are 4 three-dimensional worlds forming this lectern. But it looks three-dimensional to us because we're just highly evolved monkeys and we're just used to bouncing around in trees, and we don't need more than a three-dimensional brain for that. So I've said all of that. So now I want to talk about what Einstein really was thinking about when he was doing his thought experiments to develop relativity in the tram in Zurich. So, and what he was thinking about light. I'm going to think about light in a box. Now, this is as a paradigm to start talking about quantum mechanical wave functions shortly. So what happens when you put light in a box? Well, what I'm going to do is I'm going to get a box. It's a perfectly reflecting box. And I'm going to fill it with a green photon gas. That is a gas of green photons. And they're going to bounce backwards and forwards. And there's a lovely paper by Martin, 2019, which is referenced shortly, where he proves this works in all directions. But let's, for the sake of simplicity, imagine the green photons are going bouncy, bouncy along an axis where I'm going to either move with respect to the box or move the box. So imagine all the green photons are going in the Z direction along this box. They've got some green photons that go bouncy, bouncy backwards and forwards in the clock in the box. Now, notice straight away that I have 2 clocks. I have one clock that goes tick tock, the time of the bouncing of the photons in the box. And I've got another clock, which is the internal frequency of the photon. So one of them is measuring intervals of time, and the other one is measuring the frequency. But I've got a big clock and a little clock. Big clock box, little clock's photon. So now let's imagine I move with respect to this box. I move with respect to the box, then what I'll see that some of the green light moving in one direction gets red shifted, and in the other direction gets blue shifted. We have this red and blueness that comes if we move with respect to the box. So now if I do some maths on that, let me just do a bit of maths. Yeah, there it is. Let's do a bit of maths. If we do the mathematics of that redness and blueness, then I don't want to go too much into this. This is just the Lorentz contraction. The Lorentz factor here, gamma, has been derived by looking at the relativistic Doppler shift. The relativistic Doppler shift, the redness and blueness. If I move with respect to the box, so going back to the box, can I go backwards on this? Yeah, I can. Oh, yeah, good. There we are. If I go backwards on this, then what happens is, imagine that the scale, we're used to using h bar equals c equals m equals 1 in natural units. What I'm going to do is I'm going to say the green energy equals 1. So with respect to the green energy, if I redshift things, the redshifted part gets redshifted by r. Then the blue shifted part gets redshifted, blue shifted by 1 over r. The thing's symmetric, or it's an inverse. So that's what turns out from experiment or from the mathematics of relativity, either or, both, given that they're the same thing. So however, if one looks at the Lorentz gamma factor, 1 over the square root of 1 minus v squared over c squared, everyone knows that thing, right? Seen that all over the place. That's the factor by which space is contracted. That's the factor by which the mass changes, the energy changes. Also, it's the famous Lorentz gamma factor. A better way to derive it and to think about it is that it's actually just the half of r plus 1 over r. It's the increase in energy that the blueness gives you over the redness. Of course, the redness goes from 1 to 0, and the blueness goes from 1 to infinity. And there's much more room up to infinity than there is down to 0. You just add those together, and that's just gamma. That's all gamma is. Gamma is what happens when you have something light speed in a box. And all relativistic theories have a light speed oscillation. It's easy to solve the Dirac equation. Dirac does it in his textbook, an undergraduate textbook. And he gets a beautiful equation with okay, the exponent's a bit hard for undergrads to understand sometimes. Of course, there's There's a Dirac matrix in the exponent, so that slows them down a bit. But it's just the Zitterbewegung at light speed of the electron is the solution to the Dirac equation. It just bounces backwards and forwards at light speed in all directions. So elementary particles are light speed objects in a box of their own making. And they change relativistically in exactly the same way as does light in a box. Because they're exactly the same maths, and the maths gives the same answer. So mathematically they're the same, but also physically they're the same, because that's what they do. Hell with the maths. So let's go. Well, I've skipped a few slides here. Let me see how I'm doing for time. So 5 minutes, my goodness. Okay, well, I'll have to go faster then. I won't go back.
But then we have 15 minutes discussion.
Yes, okay, indeed. So, let me just see if I'm missing anything important here. No, that's okay. Photons in box, that's fine. No, we've done that. And this is the important thing. The important thing is this equation here. A half of r plus 1, half of the redshift plus 1 over the redshift. It's the gamma factor. There's also a simple, it's r squared minus 1 over r squared plus 1 for beta, as we will see. It's not so interesting. Right, but the conclusion of this is that confined light in a box just acts like a material particle. It just adds to the energy of the system. And I can take that box. The other thing I could do with the system, apart from, well, I could do a couple of things with this box, which are important. One is I could compress the box, squeeze the box, squeeze the green light. It's thermodynamic, it'll increase its energy. It'll get blue shifted, all the light, both so you have more and more blue, going backwards and forwards. Another thing I could do is look at the box from another frame and see red and blue. But another thing I could do is accelerate the box. Now that's different to looking at it from another frame. It's now putting a force onto it. And what happens is it bounces backwards and forwards. It's going faster and faster, but it does more bounce here than there, and that blue shifts all the light too. Increases its energy the same kind of way. But only half it, and you still get the gamma increase. Do the maths. In fact, I didn't do this maths, that was Martin. He was better at not making mistakes than me. So, and Journal of Physics Conference Series 1251, 12049, June 2019. It's, you can have a look at it. It's on the website as well. You can download it for nothing. You don't need to go through there. Right. Okay, I'll speed things up a little bit. So, right, the next thing is, so we've got a vibration, we've got an oscillation, which is what energy is. What does it look like, and how is it formed? Well, we have to go back to the person who first thought of this, which was Louis de Broglie. This is Louis de Broglie before quantum mechanics, ladies and gentlemen. He was thinking about relativity and relativistic vibrations. And he noted that if you did this, and he was worried because if you have something which you speed up relativistically, which you accelerate, then the clock should slow down according to the relativistic law of slowing down of clocks. But the energy should go up, the frequency should go up according to the relativistic law of increase of energy. So what he was puzzled about is how can you plot both speed up and slow down at the same time? But luckily, de Broglie was quite clever, quite an amazingly, the most beautiful French you'll ever read. Read his thesis in the original, even if you don't read French. By the time you finish, you'll be able to read French. It's great. It's beautiful. Well, he came up with, he realized that what happened is as you began to move things, you had two things happen. One part of it speeded up the clock, but the big clock slowed down and the little clock speeded up in such a way that if you used a ruler to mark out phase, all the phases remained the same. They remained exactly the same relationship. If something was 2.345 pi in the one and 1.762 in the other, it remained like that under the Lorentz transformation. Called the harmony of phases. And it is the way that de Broglie derived lambda is h over p for the momentum, which is what you put into the classical description in Schrödinger or Klein-Gordon or Dirac to get the momentum. That's the input that changes classical to quantum. Louis de Broglie invented it, and then it promptly got forgotten because it was easier to put the maths in, to put that little bit in lambda h over p, and then start from that in an operator than it was to really understand the quite complicated head winding stuff that it takes to understand how the harmony of phases works. So it got dropped from the undergraduate curriculum. I've met very few people, one of them's in this room, I think I've met 2 people ever in my life who knew what it was before I told them. Peter, I'm looking at you. So now, anyway, this was a big disaster because
It pays to be interested in history.
it does, and to look at where things come from, because the great thinkers are great thinkers, and you have to learn how they think.
De Bruy's French, it's the best of us.
Yeah.
You don't even need to translate it.
No, absolutely wonderful. So, right, let me just see how much more time I want to take.
John, I have a proposition.
Yes.
If there is any sort of nice cut-off point now, and I can give you half of my lecture tomorrow?
That would be possible if I was here tomorrow. But that's very sweet of you to offer. May I take another 10 minutes and we'll try and finish in
Okay.
10?
Yeah.
Okay. I may stay tomorrow, actually. I'm enjoying myself too much. But okay, so look, the thing is, and other people in this room have noted this too, there is room for improvement in relativistic quantum mechanics after 90 years. And there are, in my view, a couple of problems with Dirac relativistic quantum mechanics. The first one is his treatment of the complex number I, the unit imaginary, which must be at least quaternionic in some of the things that he's doing, at least quaternionic, as Peter was arguing yesterday. Some of us really can see there are problems here. In my view, an even bigger problem is this operator d slash. People who do this, you don't need to do this, but people who do this, d slash operator has Dirac matrices in it, divided by Dirac matrices. It's a scalar operator. It's a Lorentz scalar operator. And what it means you can write something acting on a wave function when, as the thing changes, the wave function will remain the same. Now, that might sound clever. It makes your maths easier, but it's incredibly stupid in a situation where things can transform from one thing to another, because it excludes the possibility of looking at things transforming amongst one another. One ends up with very complicated solutions called spinors, which people can't really even do. They can agree on the mathematical property of the spinors, but there's an awful lot of disagreement about what the things actually are. And the reason for this is they're fundamentally in some space which is not a real space. They're in imaginary space, but it's worse than that. So anyway, I've tried to write down equations which simplify this. They're not simple equations, though, let me warn you. So Martin and my equation is a similar equation, but it uses a vector differential operating on a multi-vector object. So it contains scalar components, but it also has cross terms, has more components. And this is, I first published this in 2014, and I've been refining it since. I'll go through this quite quickly. But I'll go through it completely quickly. I'll just skip that slide, right? Good, end of that. No, look, there's a lot of maths on this slide, and I don't expect you to go through all the maths. I'm going to try and say what it means. What I'm talking about is I'm talking about using this kind of mathematics, this vector. So I have a vector differential on a multi-vector object. That multi-vector object contains all of these space-time things that I talked about. You know, the vectors, the scalar part, the aerial parts, the trivector parts. I'm just going to say what they are. And you're either going to believe me or think I'm full of crap and not believe me, and that's fine either way. But I'm going to tell you what I think they are. So if you do this and you let it just act on the electromagnetic field part, then the mathematics is so powerful that it derives all 4 Maxwell's equations with the right signs in one line. So a subset of this equation is the Maxwell's equations. That's already a good thing. So the whole of electromagnetism is just in there, boom, bang, from the beginning, in one subset of this. What you get in addition to the 4 Maxwell's equations, when you do the full 16 components of 3 space, 3 electric field, 3 magnetic field, 3 spin, mass, the scalar, the hedgehog, which is a directed volume element, something which can either be inward directed, spine sticking out, or outward directed, spine sticking out, or inward directed, spine sticking in, less comfortable for the hedgehog. And the 4-dimensional volume element can also be directed inward or out. There are 16 components. You get 4 more equations. Now, very encouraging is the first of those 4 equations is just the Lorentz gauge. It's a gauge equation which we've been used to using for a long time. But there are 3 additional equations, The last equation is like a second gauge equation, which further constrains possible solutions. Gauge equations constrain the solutions. The Maxwell's equations are under constraint. And there are two equations that relate spin to current that look like Maxwell's equations, the spin current equations. So these are completely new. And they operate on a series of objects. Those objects are the objects I started the talk with. So I'm going to not leave that slide up any longer. I could spend an entire lecture on that slide, which I'm not as advanced as Lou. He can spend an entire lecture without even going to the first slide. But there's quite a lot in that, so I'll just lose it. I'll lose that as well. So here's the thing written out in all of its terms. So each and every term is written out here as individual terms. So if you're multiplying a 4 derivative by 16 components, you know how many you're going to get, right? 64. So there's the 64 components. But if you look at them and you look at the patterns, you can write them as the equations that you're familiar with. So there's a differential of the electric field plus the curl of B is equal to 0 if there's no mass. It's just a Maxwell's equation. So, so what we have is we have in this thing, we have complex rest mass, P and Q, P at the top, Q at the bottom. We have the electromagnetic field, the E's and B's as normal. And we have this very important new part, the trivector part, which is like a momentum going round and round in circles. So that's the direction of angular spin. It's the intrinsic spin. This is a completely new thing about the theory. The theory describes spin microscopically. So what does this do for? Okay, that's maths. I'm finished with maths. Okay. What does this do for the world we live in? And I'm nearly finished the talk as well. Right. There's no escaping the relativistic world. The relativistic world is what forms us and the world we live in. And these things are quantized, and they're not just quantized in one thing. All the quantizations happen at once. Why? Because they all flow around quantum wave functions. They flow into one another. The even part of the algebra is related through a linear differential with the odd part of the algebra. That means the even part precisely constrains the odd part. And likewise, the odd part precisely constrains the even part. These things flow around the circuit. So you have quantized energy, quantized time, that's energy, quantized space, momentum, charge, electric interaction, quantized flux, H over E, magnetic interaction. You have quantized conductance, you have derived quantizations. They all happen at once. You don't get just one of them. They're all there, bang, straight away, because they're all part of the structure of the underlying space-time. You get quantized. Okay, we also get quantum mind, because I think it's becoming more and more clear that our brains are quantum computers, far more complex than anything we can make. And you also get quantized people, because we come one at a time. That's what quantum really means. So I was going to talk about, I don't have time.
No,
I don't have time.
No.
I'll just say one thing, which is that these flows flow into one. Oh, I said that. Okay, let's just go to conclusions. Ding, 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 ding. Conclusions. Down here somewhere. Did I go past the conclusions? No. Ding, conclusions. Right, so conclusions. Everything is connected with everything else. All things are intimately connected through the interactions that we have with everything else. The universe we live in, if we go from Newtonian to relativistic to quantum relativistic, you go from 3D to 3 plus 1D to multiple 3D spaces. The 3D spaces are space, electric field, magnetic field, and spin. The 1D spaces associated with that are mass, time, the hedgehog, directed volumes, like a charge, and the quedgehog, which is the quantum hedgehog, the 4-dimensional thing. These things are all put together in a series of, which I didn't say, is that the base form is a quaternionic form. If you start with a quaternionic form, which is one of these 3D spaces, and multiply it by the 1D spaces, you get a set of copies that are not quaternions, but that give you the other spaces, the spin space, the electric field space, and the magnetic field space. I meant to say that, but I missed the slides out that said that, I'm sorry. That is true. The mass and the dual mass, you can gather them together, they're isomorphic to complex numbers. So there's a mass field there, like ordinary quantum mechanics. and they flow between one another. You can have flows there, wave functions, but you adjust that, which is just like Schrödinger's wave solutions. But although the universe is far more complex than simply 3D, it appears and acts in a completely three-dimensional way because it's composed of multiply three-dimensional spaces. And that's the end of the talk. And thank you very much for listening. And I do apologize for not timing it properly.
May I suggest that we check the Zoom, because you can buttonhole John.
I'm sorry.
I say I check whether there is anybody on Zoom before.
Oh, yeah.
Is that all right? No, Luke?
Okay. I was wondering how you handle cosmological issues, black holes, things like that from your point of view.
Okay. Well, the theory itself is not dealing with Einstein's general relativity, which is a beautiful theory on top of all of this. However, I do have opinions about these things, very strong opinions about these things. It's not part of the quantum locality here that I talked about, the black hole, but I think it's worth saying that the black hole equations are really hybrid equations. They're partly classical and partly, partly general relativistic and partly non-relativistic. And I have seen and have been convinced by papers, especially by Stephen Crothers, who's done a fully general relativistic analysis, and by Viv Robinson, a colleague in Australia.
Now, I thought that maybe you have a point of view about Hawking radiation.
I think it's complete enough. I think it's not. I don't think it's happening. That would require a sharp boundary. I think as you move towards the boundary of the apparent boundary of a black hole, it shifts. There is no sharp boundary if you do the thing properly, general relativistically. There is if you do it with the hybrid system, and then you have an approximation, and that seems. So I think Hawking radiation is a thing within a particular theoretical framework, but I don't think it's a thing when it's done properly, in my view. And I must say that I'm not an expert on that, so I wouldn't be able to sit down and write down the equations and show you where it went wrong. But Stephen Crothers was the first one I saw who did that, and that was quite. Are you familiar with the story behind this? He was doing this for his PhD at an Australian university. The university withdrew him from the program, and he didn't get his PhD.
Why did they withdraw from the program?
Too controversial, young lady.
It was contradicting Hawking.
Really?
Who was that?
Stephen Crothers.
Oh, I remember him.
Yeah.
He's had a lot of trouble.
He's had an awful lot of trouble. It's an absolute tragedy. And
If anybody's ever
totally,
been cancelled,
it's him. Yeah, absolutely cancelled from the beginning. University just didn't want to be
Which
associated.
Which university was it?
Some shitty, not to be mentioned. I wouldn't say the name if I could remember what it was. In Australia.
Yeah, before Mike faints,
Yeah.
can you give him hi, Mike?
Um,
Mike Corner. Yeah.
hello, John.
Yeah. Hello, Mike.
I have a question, but I need to know whether you saw my talk on the other day.
I did.
Okay. As you know from previous discussions, my sort of starting point, which in fact is very, very close to yours, unfortunately brings in this concept of information, which I raised to the same level as matter and energy.
I think it's a higher level, Michael.
Okay, let's, if you like, agree that what you're doing is a fantastic piece of work, but I would argue that at the very first step, because you did not include information, and if you were to just slightly adjust the terminology of my work, then I'm proposing information, which is entirely a new use of this word, unfortunately, is in the space, which I call space of dimension -1. And otherwise, we are getting very close, except that you are interested in using all of your excellent work in describing what is the relationship between the entities in these two spaces. But I'm more interested in the entities and their, call it negative equivalence in the -1 space, where we then get into more mysterious things like how does the mind work, not the brain work, and consciousness and stuff like that. So your equations are unbelievably helpful, but they only deal with half the story.
Mike, I could not agree with you more. And let me say a couple of things. I do disagree with some of the nomenclature. I wouldn't call it a -1 space. I'd call it a 0 space. And the reason for that is that I think that what happens is when you have, I haven't given the talk on my interaction talk. That would have perhaps fitted in better with what you just said as well.
Well, look, we don't have a lot of time to talk about this, and there may be other questions. I'd like to just lay one on you, a very important feature of my evolving scheme, again, work in progress, is that the two spaces compare each other, and you led me to the understanding of jitterbug wagon, and
Jitterbug is better. I like it.
the result is kept in this new space, and so evolution progresses by keeping a record, but only of things which are acceptable within some sort of limits. And I think that is a feature not included in the way you've talked about it, because you've only really focused on one space so far.
No, I wanted to give a talk today about one thing, which is how relativistic. So it has been necessarily a really limited set. But I agree with Peter, for example, and many others, that the entire universe is really of energy 0. And what we're looking at, and we have to find a way, and for me that way is in the of making sure that the mc² energy, which is very significant, is cancelled. And of course the idea is that gravitational interactions would cancel that. But I see these as interactions, and these interactions are indeed in a negative energy space. So you have the space of the thing that acts and thing which is acted upon, but then the space between those is something which has to carry this negative energy. So, but that's a much longer talk, or series of talks.
Right. Can I cut in, because we have time for one more question? Albrecht, I see you raise the hand, and we need a short break before Lou's talk. Okay. So Albrecht, and then.
Yeah. Okay. I would like to make a comment to what you said about the harmony of phases of de Broglie. And I think, and I've also discussed it earlier, that de Broglie is in a great error here, because he is seeing the conflict between an elementary, the internal oscillation of a particle, which moves by dilation, but it has to increase by the fact that the energy of a moving particle is increased, of course, due to its motion. But this conflict does not exist. De Broglie has misunderstood the Lorentz transformation because with respect to dilation, but I can explain it in I think a more easy way. Assume you look at a particle which moves towards you. This particle has an internal oscillation.
I think that's a non-concept. I think that's a non-concept, Albrecht. It's particle, first of all, particle, I don't think it's a proper concept. Secondly, moving smoothly, I don't think is a proper concept. Thing has to go backwards and forwards. It must.
Yeah, but the particle is, yeah. Okay, may I continue? You have a particle which has an internal oscillation. That is what de Broglie is talking about. And this particle, if it moves towards you, has dilation, of course, undergoes dilation because it is in motion. But when it meets you, you will see an increase of frequency due to the Doppler effect, because the waves which are connected to the oscillation arrive you in a situation where a Doppler effect works. And if you now compare mathematically the dilation, now you combine the dilation with this Doppler effect, you get exactly the result which you have with the Planck relation between energy and frequency. So that works perfectly, and there's no need for de Broglie to invent harmony of phases or something like that.
Albrecht, are you saying there's no need for lambda is h over p?
I did not understand, sorry. What did you say?
Are you saying that there's no need for the de Broglie relation? Lambda is h.
There's no need, and it is wrong in the result, because if you apply it to a moving electron.
Years, that's nonsense.
Right. I see we are getting into very controversial field. Nicola wants to say something. Whoever is not involved in this controversy, please go and have a quick break. and John and Albert, maybe you take it offline.
Oh, okay. Oh, yes. No.
Not to make us uncomfortable. I'm really sorry.
Okay.
Okay, thank
No.
you.
I just wanted to ask like a really quick thing in terms of some of the energy space being zero. Can it have direction still?
I don't think it has a direction because it's a space which is zero dimension. Yeah.
It's absolutely
It's nothing.
nothing. The,
Well,
the whole thing is nothing.
There are things that can have direction.
yeah.
Maybe the hedgehog, the hedgehog and the hedgehog, they can have direction.
Well, they're within
Yeah,
zero. They're not
Yeah.
extra to it.
But we're saying if we're looking at an information level, whether that
Well, yes, I mean, space is crisscrossed. It's not full of space, but it's crisscrossed by this exchange of information. Because the exchange of information is instantaneous to the photon.